All right. Okay, so um, turns out we had some microphone issues. We switched microphones, so I hope this works. Let us know if it does. In the meantime, our tech guy is double checking everything as well. Nevertheless, I would like to get started. I'll start over again just to make sure that you were able to hear everything all right. So welcome everyone to this live stream of Engineering Trainer TV. My name is Luuk Hennen. I'm the CEO of Engineering Trainer. And today we will have a conversation with Juan Manuel Mendez Franco, who is the COO at Stressman Engineering and also the president of the PSI Association. Um, Having said that, Juan, it's an honor to have you. How are you doing?
I'm super good, really happy. It feels funny to get to know you for the first time in person. We've been talking for a few months now, and it's just an honor. I really like your facilities. You have a very beautiful office. I love your desktops downstairs, the ones that they can go up and down, and you can walk standing or you can walk in like in the chair. So it's pretty nice. Beautiful studio as well. So I'm happy to be back in the Netherlands. I think this is
Awesome.
my third or fourth time in the Netherlands. So I love to be here. Love
Thanks.
to be here. So happy.
All right. Well, it's an honor to have you and great to meet you in person as well. Um, Having said that, today Juan and I will be discussing primary versus secondary stress, analysis and considerations. We basically took a set of slides that we found like was an interesting topic from the Introduction to Pipe Stress, Fundamentals 1 and Fundamentals 2 course that Stressman Engineering is providing on engineeringtrainer.com. So, you know, if this topic could be of interest to you and your team, please feel free to check that one out. Um, we'll roughly take, we'll aim, let's say, 45 minutes. We might go a little bit longer depending on the amount of questions that we get from you guys. And having said that, I would also like to welcome everybody and also welcome you to participate in the chat. So if you're listening, please take a second to open the chat in YouTube or in our portal if you're viewing it from there. And make sure to let us know from which location around the world you are tuning in. It's always nice to connect with you and interact. And also make sure to connect with me and with Juan on LinkedIn and shoot us a message if you feel like. Having said that, Juan, I mean, maybe you can introduce us a little bit about who you are, and also like you've been making quite a trip through Europe for the past, I would say, month.
Month.
Maybe you could tell us a little bit about that.
Yeah, that's fine. Well, I'm so happy to have you here. Let's see if you can. Can you see my screen now? My name is Juan Manuel Mendez Franco. I'm piping stress engineer. I've been doing piping stress analysis for 17 years now. I would say that my main expertise is related to oil and gas projects, petrochemical facilities, LNG plants, which is the type of projects that I really love. And I think
Right.
right now it's quite up in the market. You know, there's so
Yeah.
many LNG projects around the world happening right now. I think it's also quite interesting the part related to the supports, the LNG supports, special type of consideration that you have to have. So I'm really like interested in those type of projects, you know.
And,
Um,
and where have you been in Europe, or you might get to that later?
yeah, and
Awesome.
I'll show you this one. This is kind of funny because I got it today from I think it's from Google Timeline that it shows you the places that you have been during the month of June. This one, does, for example, doesn't include Colombia, which is where I'm located during the past few months.
All right.
But I've been to Mexico, having meetings there with some engineering firms, also some nice meetings in Spain, Técnicas Reunidas, EPSA, some of the meetings in Germany with the guys of Lisega, that is the company, the pipe support company that we now represent in Mexico and the state
All
of
right.
Texas. And I really had a very, very good time there. They have a state of the art facility. They treat me like super, super well. I had a great time. I also met with the people from Vertical Support, which is the other company that we represent as well. Now we're going to represent them in Mexico and Colombia. They have also very, very nice facility. Thomas Bernicke, the owner, is super nice guy. So I had a good time. I got a chance to visit my friend and partner Sondre and experience some of the Norwegian lifestyle.
All
You
right.
know, it's so nice that the weather is so perfect right now. According to them, we had the best days during the year when I was there.
Yeah.
So it was sunny, it was even hot. I never thought that it was going to be that hot. I swam in Norwegian seas, which is quite amazing because I never thought that I was going to be swimming in such a cold water, but it was
Yeah.
fresh water. So it was nice, very nice trip, and everything thanks to, to all the stuff that we do about piping, which is our passion and what we love. So just to begin, I would like to start with a quick introduction about who Stressman Engineering is.
Yeah.
And I really love this slide, which I call them the logos, the Lego slide, because it's kind of like quite nice in my opinion. And this is what we can do. We can do laser scan, high pressure vessels, offshore projects, onshore, eolic projects. We represent a few companies that also manufacture supports, others that
Right.
manufacture expansion joints, other one that manufacture valves. So pretty much is we're trying to provide all the solutions related to a piping project or to a stress analysis project. The main expertise that we have in Norway is related to FEA and CFD, which is something that I really like. When I get to have the opportunity to see those projects, I'm quite happy. More than 400 projects around the world. These are the different organizations that we represent, the PSI Association or We Energy Partners. Like I said, we're happy to represent Flexi Latina, expansion joint manufacturer from Colombia.
All right.
And well, the other companies already mentioned, Cornerstone, Severe Service Valves, and what I would like just to finalize this part is we can help you with any type of projects related to piping or stress analysis or fluid dynamics. I would also like to invite you to join or to send me an email in case you are interested to be part of ASME 313. I'm now also part of the international committee group. So feel free to send me an email in case you want to be part of this really interesting group.
All right.
And well, I think that would be the main presentation about the Strongman Engineering.
All right, all
Hmm.
right. I mean, thanks for that introduction. If you
Yes.
want to connect with Juan directly, I think one of the best ways is to just shoot him a message on LinkedIn. I know you're rather active on there. Having said all this, let's move into the topic. Primary stresses versus secondary stresses. Um, like when I started as a pipe stress engineer, that was back in 2012. Primary and secondary stresses, it took me a while to really get wrap my head around those concepts. And I know from interacting with all the users on our platform that they experience the same thing. It can be quite a confusing topic. So today I would like to discuss it with you a little bit, hear your take on it, hear some insights.
Hmm.
Um, Maybe you can give us a little bit of an introduction about these concepts and jump into primary loads as a starter, and we'll go from there.
Yeah, that's perfect. That's perfect. I think I'm gonna share a few slides that I have. Mhm. As you know, these slides are coming from our training, our presentation, the piping stress fundamentals, the
Yeah,
course that we have online with engineering trainer. And I think this course is about the fundamentals, the foundation of to really understand how piping stress works. What is it? Why is it important? And what's the main consideration that you have to take into account to become eventually a good piping stress engineer?
right.
Mhm. So I would say that when we go to engineering school, you see the stresses as just uh, not something that you have to compare against a code. You
Yeah,
just do stress analysis of, let's say, of a gear, for example,
yeah,
which is
yeah,
like a completely different component,
yeah,
not a pipe, and then you compare, you use those stresses. But I don't know, at least in my experience, when you're in the engineering school, you don't compare it against a code. It's just, is it going to break? Is it not going to break? Is it
yeah,
going to
yeah.
fail? Is it going to be mm, working or not? But here in piping, we have codes, and the codes are to regulate the way that we do and perform or execute our calculation.
All right.
It's kind of like a go by to play on the safe side. That is also guidance for younger engineers or for also for experienced engineers, but also to standardize the way that we execute the project.
Yeah,
So uh, at the beginning, we have the primary loads, which is what is shown in this slide, which is pretty much coming from the result of weight, and the internal pressure. I would put it like that as the basic part, the weight of the pipe, weight of the fluid, and the weight of the insulation and the internal pressure,
Right.
which
Yeah.
in this case, if we use our software, it would be W plus P. That's
Right.
our
Yeah.
primary loads. Then we have the secondary loads, which in this case are the expansion, the temperature, the thermal expansion or the thermal contraction that you can have in a piping system when it starts to operate.
Right.
Here you can also have other type of forces because these are related to displacement. The other ones are related to forces. These are displacement driven. In this case, you can also have deflection due to hogging and sagging on your supports, for example, in an FPSO,
Right. On a ship. Yeah.
on a
Yeah.
ship. So that's the second part, and we don't compare them the same way, just like the third one that we have, which is the occasional case. But this is not the one that I'm going to emphasize today, but it needs to be part of this conversation,
Yeah.
obviously, because it needs to be taken into consideration when we perform a piping stress calculation. The third one, occasional, as it names it's already saying, it's something that happens occasionally. It could be earthquake, the accelerations. You have to include those accelerations.
Yeah.
You have to add wind in some cases. It's something that is not happening all the time. And I would say it could be like the other one could be when a PSB goes off.
Yeah.
That's
Yeah.
another occasional case. And there are some other cases, but for now, these are what I would say the most typical cases and the most typical combinations that you have when you do your piping stress analysis.
Right.
Why do we have them in three different groups, primary, secondary, and occasional? Because each one of them is going to be evaluated and compared to the code in a different way.
All right.
Because if they were all the same, we can just add the three of them and compare, I don't know, one is one, the other is two, and the other is three. We have six. The code says that maximum is five. We fail. But
Yeah.
no, you cannot combine them like that.
Yeah.
That's why we separate them from the beginning. So now we evaluate each one of them, and I think it helps to understand where each one of the issues on your piping system is coming from.
Exactly. Yeah. Yeah. So now feel free to continue. Yeah.
Okay. So for example, here we have the primary loads. I really like this picture. I really, really love it. It's so shiny. The render is just pretty.
It is. Yeah.
And I would like to say that, as you can see here, these are imposed by loads. You know what could be the load? The weight of the valve, for example. If you have valves, if you have flanges,
Yeah.
they are not self-limiting, and they continue until equilibrium between external and internal loads of the piping system is reached, or until, which is the bad part here, catastrophic rupture of the pipe occurs, when the system collapses. If it's not properly supported,
Yeah.
it's going to collapse. If the wall thickness is not accurate, it's not well calculated, it's going to collapse. Here, I would say, now we're going to start talking about the piping stress analysis perspective. When we receive a calculation or when we receive a system that needs to be analyzed,
Yeah.
in a big project, I would say at the beginning, someone else, a piping engineer or a piping materials engineer, is going to do the wall thickness calculation. He's going to give me a pipe specification that I'm going to use, and I'm going to input that information into my piping CSAR calculation or piping stress software.
Yeah.
I'm going to say this is the diameter, this is the wall thickness. You would say that you don't have to worry about the wall thickness calculation because that was already done.
Right. Right.
Of course, it could be wrong, but in general, let's assume that it was correct.
As part of the pipe spec, I would say. Right?
So
Yeah.
for us, the main thing would be to think about the weight. What do we have? How are we going to support our system so it doesn't fall,
Yeah.
it doesn't collapse? One of the important things is I would also say that from the piping stress perspective and from the project perspective, this a piping system, when it comes to a piping stress engineer, it should already have support, which means that the piping designer, when he route the system, he's already going to identify the locations of the supports. He's going to put at least maybe in some cases a mark
Yeah.
that
Yeah.
you can know that okay, there is a point of support here, a point of support there. Or if he goes beyond, maybe already has a shoe or a tronion, depending on the need. But he already identifies those point of support. So when he sees the system, he can use, like thumb roll
Yeah.
to say, okay, these supports are enough for my primary
Yeah,
primary loads.
like his engineering judgment, I would
His
say, right?
engineering judgment,
Yeah.
which is, I would say, what he would use to estimate how to support the system.
Yeah.
I think this is quite nice. It's a quite nice graphic to show how the primary loads work. Here we have, as we said, first driven. Once plastic deformation begins, it grows rapidly,
Yeah.
and the failure can occur with single application of a load. Let's have a look at this. I really like this. You have a weight, for example, let's say it's 100 kilograms. This cantilever beam is going to deflect, I don't know, let's say 10 millimeters.
Yeah.
As you can see in the graphic, I'm going to try to highlight it here as well. Uh, oh, just a second. As it's shown there, it's going to strain, uh, you know, so much that if you double the weight,
Yeah.
you double the force, it's going to strain twice as much.
Right.
As you can see, stress is also twice because we're working within the elastic zone,
Yeah.
which means that it's going to be linear, according to Hooke's law. Mhm. And then for the third one, let's say that we add another weight. Now this third weight, this that is now 100, 200, 300, it's gonna go beyond the elastic behavior, and now it's gonna start behaving completely different.
Right.
So right here is when it collapses.
Yeah.
It is just it's just so simple to see, so simple to understand. If you have a look at this other part right here, at this image, it's not showing it. Just a second.
No worries.
Right here,
Yeah.
as you can see, the little deflection that you have on those elbows due to the weight, because as you can see, the supports are right here, and the other supports are here, and the others are here. So this section here is just deflecting a little bit
Yeah.
because
Yeah.
of
It
its
keeps
own weight.
sagging a little bit.
It's sagging. So if that weight was really, really big, so it would just collapse. It would just fall.
Right.
That's the way that it works. I would say, just to simplify everything for everybody, somebody said, "Oh, let's do some pipe span tables," and here everything, some different values are taken into consideration, just like pipe size, thickness, material. There are multiple variables that we have. The density is so important as well.
Yeah.
Whether if it's a fluid, let's say full of water, or if you're going to support a line that is just with vapor, gas,
Yeah. Yeah.
density is going to change. And at the end, you're going to have your span for a straight run of pipe, for some configurations, quite popular configurations like a horizontal run, or like in a XYZ
Right. Yeah.
direction.
Some different routings.
Different
basically, right?
routing. These are kind of standard routings. If you see here also, this one is for 200 Fahrenheit and below, and this is from 200. This one is from 200 to 600 Fahrenheit.
All right. Yeah.
Also with uh, the pipe span is going to change. It's going to vary depending on the temperature. So there are multiple variables, but I think you can always use this type of tables just to make it easier for everybody. So
What kind of limit is used in these tables?
I would say this one in general is like 5/8 of an inch of sagging. I think that
Yeah.
would be the standard. Maybe in some other companies they could be more stringent. It really depends, or they could also be a little bit more flexible. And at the end, it doesn't mean that, oh, if you are exceeding 5/8 of an inch, yeah, it's going to fail. No, it's still okay. I mean, that's why we have to use the engineering judgment. At the end, these are just recommendations,
Yeah.
not because it says that the maximum span for a 2-inch line is I don't know, 8 feet.
Yeah. Exactly. Yeah. Yeah.
What if you have 9 feet? No, it could be okay, no problem.
Yeah.
So that's why it's important that we know this. And like I said, this training is, or this presentation is the fundamentals. This is the basics. So we at least when we start getting into this topic, we know where is everything coming from.
Yeah. So
Hmm.
just to summarize, like even if you would be using a span length that would be a little bit longer, like technically your primary stresses could still be okay. But I mean, depending on the project, whether you're allowed to or not. But that is how it is organized, if I
Hmm.
understand correctly. Based on this introduction about primary stresses, I mean, I would like to ask just like two basic questions, just to get the basics understood really well. Is so let's say you would have you're doing a stress analysis, and in your stress analysis it shows that the primary stress is much too high. Let's say 500%, like crazy amount. You ignore that, and the system would be built. So what would actually happen?
Well, when it's something like that, well, that much, I think it would just collapse. I mean, it wouldn't even be able to stand in
Right,
place.
right.
I cannot even imagine what could happen, but it's just that it cannot be together for too
Yeah,
long.
yeah, yeah, yeah.
Uh,
All right, but I mean, yeah, I mean, basically, like, it just collapsed due to plastic deformation,
yes,
right?
that's it. That's it.
That's what would happen
Hmm.
in the steel.
Hmm.
Yeah,
Hmm.
yeah. All right. So having said that, so then, what is like the general methodology, like stating, um, to solve high primary stresses? Like, what is the general approach people take?
Just to add more support. I mean, at
Right.
the end, I think that's like the basic, the easiest solution.
Yeah. Yeah.
And obviously, the other one will be to increase the wall thickness on the pipe. It,
Right.
it can
Right.
also help because maybe the issue is not coming only from the weight. Maybe there is something wrong with the pressure with the calculation, and now if you increase the wall thickness in your pipe, or you go to the next rating in your specification, then okay, problem solved as
Yeah. Yeah.
well.
Yeah. All
So
right.
because at the end, it's not just weight, but it's also pressure.
Right,
Hmm.
right. So adding supports if you're evaluating weight, making sure your thickness is is sufficient
Hmm.
to suffice with high pressure, which is also a primary load. All right. Okay. So maybe we can now jump into secondary stresses.
Here, for example, uh, secondary loads, I would say in general, they are related to displacement. Displacement, it could be to sagging and hogging, like I mentioned earlier.
Right.
It could be matchup tolerances, a little bit of, fabrication, settlement, that's another option. But I would say, again, for this particular presentation, let's just think about the thermal expansion,
Right.
the
Right.
temperature, the change in temperature from the initial position to the, let's say, final position.
Yeah.
When you have your T, your temperature, and then you are adding that delta T, and now your pipe is going to grow delta L. Something really simple,
Yeah.
very basic. When you have this type of stresses, they are going to be localized. It's when they fail, it's not the entire system that is going to fail. It's just in a section, like fracture in a component, fracture in an elbow. Maybe if there is a flange close by,
Yeah.
it's going to be subjected to a large bending moment that it's going to start leaking.
Yeah. Yeah.
That kind of stuff. I mean, it's kind of like simple, but that's pretty much the secondary loads. This is a good example as well. Again, this is displacement driven, like as I mentioned.
Yeah.
Once the deformation begins, loads tend to dissipate due to local deformation, which is
Right.
that I'm going to show that here. And the failure occurs after several load cycles. It's something that may be fine the first time, but over a period of time is just going to fail.
Yeah.
We have here delta T, let's say, again, using an easy number, 100 Celsius. Mhm. That's the deformation you're going to have, the E, the strain, and the forces. Now you add temperature 2,
Yeah.
which is twice as hot, let's say another 100 degrees, 200 degrees, and it's still within the elastic behavior. I think you cannot see that, but I think now you can see it, elastic behavior.
Yeah.
And well, everything is going well right there. But then we have this one here. Well, now it goes 3 times E, and now it's 300 Celsius, let's
Right.
say. Now the 300 Celsius we were passed beyond the elastic behavior, and it's supposed to go to the plastic behavior. So, but the stress that we're calculating here is not a real stress,
Yeah,
because
yeah,
at the end we're not using the stress strain curve that we normally use, but the code allows us to do this.
yeah,
Mhm.
yeah.
And I think it makes it easier. And at the end, it's because these uh, stresses are going to happen not in the entire system. It's just in a specific location,
Yeah.
and that's why it can work that way.
All right.
Here, for example, we have some uh, examples about thermal expansion and how it behaves in a piping system.
Right. Yeah.
It's always important to take into consideration the growth, the thermal growth that you're going to have in your system,
Yeah.
and you don't have issues like this,
So
where,
what do we see here? We see a piece of piping.
yeah, for example, here you can see a shoe that because of thermal expansion is moving too much. Now, because it's moving too much, it fell of the steel,
Right.
you
Right.
know. I would say maybe this is not such a big deal. It fell, it's going to be resting on the insulation. But what happens if this tries to go back to its original position?
Right.
Now there is going to be a force that is going to try to go the other way, that it may,
Basically, an actual stop,
yeah,
kind of.
it's like an action stop but in the one direction,
Yeah.
because if
Yeah.
it goes the other way, it's still free to move. So those are the kind of issues that you have to take into consideration when you are looking at your thermal loads, which in
Yeah.
this case are our secondary loads.
Yeah. So what do we see at the top image?
Here at the top, we have an example about a loop. Mhm. When you have guides and when you don't have guides. At
Okay.
the end, I think this is the main part about secondary loads. Secondary loads, what they want is flexibility.
Right.
Primary loads, what they have is restraints. Restraints just to keep the pipe in place, it's not falling. With the thermal expansion, it's the opposite. They want your system to be flexible. So to be flexible, it means less restraints.
Right. 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 Right.
Excuse me. So in this particular case that we have here, oh, my voice is getting a little bit bad.
No worries.
The example in the top, this deflection without guide support, as you can see, the stresses probably here are going to be lower because we're pretty much letting the pipe do whatever she wants to do.
Yeah.
I'm
No
sorry.
worries. Take a second.
We are letting the pipe to do whatever she wants to do. In the second one, we have now horizontal restraints, lateral restraints, and now we're gonna have higher stresses, perhaps near these elbows. Right. Oh,
Oh,
we're gonna have higher stresses maybe near these elbows or somewhere here. As you can see, the other one is much more smooth,
right.
smoother.
Yeah. Yeah.
So the pipe is free.
Yeah.
So
Is one better than the other?
I mean, both can work. Now the thing here is, in the real life, we not only have primary and secondary loads, we also have occasional loads.
Right.
Mhm. So what about this system in case that we have, for example, wind? Mhm. So let's look at this one here, the deflection without guide. If we have wind in this direction, this is just going to keep moving. And if it's moving too much and we don't have any restraints, it may overstress. At some
Exactly.
point it's going to have a restraint. Let's say here it has a restraint. At some point it's going to be overstressed. Or if we let it move too much, it may hit a pipe that is adjacent to it,
Yeah. Yeah. Yeah.
right next to it. That's why we sometimes we need to add this other guy, and then you make your loop work. So now it's working, but at the same time you are protecting your system against the wind. which in this case is the occasional load. So at the end, both work in this particular case, but one will also solve issues for an occasional load.
Yeah.
The other one may not, but perhaps it's in an enclosed location, or perhaps this location is protected, or it's in the shade, and it has a shade, and it doesn't affect the wind, doesn't affect the pipe.
Yeah. Yeah.
So there are multiple options. So, but I would say in general that's what is happening with the primary and with the secondary loads.
All right. All right. I mean, we have one image left on the bottom right. Maybe we could address that as well. I mean, there's two expansion loops, obviously. Maybe again the question, like which one is the best one? What is the difference?
Well, this one is also interesting. I mean, both are options that you can have in a piping system. The first one is, as you see, it has four elbows. With the four elbows, it's gonna have less flexibility. It's more rigid routing. This one has six elbows, so this is a lot more flexible.
Yeah. Yeah.
The thing is, in this one, the one right here, in some cases you cannot have a flat turn because there are more pipes that are right next to it. That's why when you are in a pipe rack, you have multiple levels. So in the first level, there's lines running north-south. Then in an intermediate level, you have lines running east-west.
Yeah.
So you go up one level, then you go across, then maybe you can come back and then go down. So without interfering the other pipes.
Yeah. Yeah. Yeah.
You can have the horizontal loop as well if you are in the edge. I mean, it's possible too. Or you can have horizontal loops when there is just nothing around.
Right.
There is no need to have the vertical component for this expansion loop.
Yeah. Yeah. Yeah.
Just something simple.
All right. All right. So just to jump on this topic a little bit, I'm just asking the same questions as I was for primary stress. So just to summarize, if you want to tackle high primary stresses, you are adding supports, and like if you wouldn't do that, then collapse would happen, right? Plastic deformation and collapse. So now let's say you're analyzing secondary stresses, and you find in your system that there's like a really high number at some point, and you ignore it, and the system would be built. What would actually like physically happen?
I didn't
All right, so let's say you have high secondary stresses in the system, right? And that system would be built. Like what would happen?
Yeah, that one is more, in my opinion, is more likely to happen. When, and not necessarily because there was a mistake from the piping engineer, but there are facilities that were built, I don't know, in the 70s, in the 60s, and they want to increase the capacity of the systems, and now they are adding, increasing the temperature for some lines,
Right.
or well, also obviously the velocities and the capacities of some of the machines that they have over there. So now the pipe that was designed for, let's say, 200 Celsius, now
Yeah.
they want to run it at 250 Celsius.
Yeah. Yeah. Yeah.
So that little delta, it could be of great impact in a system. Maybe the line when it was designed was 90% capacity, 90% of the utilization.
Yeah.
Now with this, it's probably going 110, and it's going to fail. What happened? There could be fracture in whatever, like the component, or like what we said before, near the introduce of an elbow.
All right. Yeah. Yeah. Yeah.
Like we also mentioned, to bend a flame so that it's going to start
Yeah.
leaking.
Yeah. Yeah.
I mean,
So typically fracture. That's what you're
fracture,
saying, right? Maybe like
yes.
in welds or items like these. So like where gross collapse in primary would happen like instantly, like if it's not supported, it would just collapse because of plastic deformation. I mean, this if you install it and you take it into operation, like this crack wouldn't be there all of a sudden. Like it would take like some cycling.
Yeah. Mhm.
All right. So having said that, so reducing primary stresses, the methodology was, adding more supports like rigidity. What is the solution to reducing secondary stresses?
To have less supports, add flexibility to the system.
Right.
I mean, let me correct that. Not necessarily less support, but adding more flexibility to your piping system.
Right.
So that's why I think, just to finalize with this conversation, I think we can encapsulate everything with one word: balance. I think that's it's a beautiful word. I think that turns piping stress engineering in something that I feel more like an art. To put it with nice words, with the romantic words, more like an art, where you have to find that balance between having those restraints supporting your line for the weight, what everybody can see, or it's just to support it, have enough support,
Yeah.
so the pipe doesn't fall. Then you have the step two, the secondary loads, where you want to restrain it and add flexibility. I would say in general some horizontal restraints, but you can also have thermal vertical expansion. For example, in a line that is coming from a tower, or that it's going to a different level in the pipe rack.
Yeah.
That's also important, but it's in general to have flexibility and have enough restraints as well, so the pipe behaves the way you want. And the one at the end would be the occasional, which
Right.
is you now have enough flexibility, you have enough support, but now you have this guy, the third one, which is, I would say, like the bad guy, the bad stress, because it's a stress that with these two it would be just fine. You find the vertical supports, horizontal supports, but now you have the bad boy, and this guy is like, oh, I'm gonna move more than what is the the thermal expansion is going to move. So now the restraints that may work for secondary loads may affect you. And in the third case, would be occasional loads, or
Exactly.
vice versa.
Yeah.
So at the end, it's to do that fine tuning between what do I need to do to protect my system due to wind, earthquake, that is also not going to affect my horizontal or thermal expansion.
Yeah.
Find that balance, and to support my line properly in the vertical position.
Right. Right. So
So I think that's once you understand that part, and you find, you have that experience and get that feeling on how to support your lines and your system, it's when you become a piping stress engineer. That's what I see.
all right. I mean, I love the analogy with art. Like, okay, so just to summarize about this balance, if I understand it correctly, so you basically have like supports. You're adding supports for the primary loads. Then you're making sure the flexibilities are right for the secondary loads, which are like sometimes you have like you want like more flexibility, and then comes along the occasional stresses, okay, due to occasional loads, and those require a lot of more sports again. So you have sports, flexibility, supports, and balancing those.
Exactly,
That is what
exactly.
it's all about.
Yeah. So that's what it's all about, and I think that's why this discipline that we have, this part of the mechanical engineering that we work on, is so nice, because you will never find the same piping system anywhere. It's always going to be slightly different. You always find new challenges. You always find new routings.
I would also say that the third one, occasional, that's where well typically most of the challenges arise, right? Like weight checks are typically done rather fast due to spine lengths and experienced piping designers. Then you have flexibility, the secondary stresses, but then adding those like earthquake, like wind, that's
Yeah,
where the real struggle starts, right?
yeah. I mean, it could be in different cases, because right now we're just thinking about those stresses, but at the same time we also have to verify loads. For example, loads in nozzles.
Right,
And
right.
sometimes the issues for wind and earthquake are not so bad with some pieces of equipment. The main issue could be the thermal expansion,
Yeah,
because
yeah,
that becomes some kind of anchor, a fixed anchor, and dealing with fixed anchor sometimes is when you get like heavy loads. So it's that's the nice part again. Now, in some cases, you have to deal with temperature. In some other cases, it's worse to deal with the occasional cases such as wind or earthquake. There is just one support that works in one of them and not in the other, which is the snubber. The snubber, it's kind of safety belt that moves along the pipe with the temperature. When
yeah,
it's
yeah.
smooth, it moves up and down like if there was no restraint. But the moment you have an earthquake, or you have, let's say, water hammer, it's a sudden movement, a sudden reaction. It locks up.
Right.
So that one, it works only for occasional case, and it's a horizontal restraint. It could also be vertical restraint, but that's the only case. Other than that, all the restraints that you have for your piping system are going to work in your three different type of loads.
Right.
So, and those, I think we also have the experts, Lisega. We have Snovers with Lisega. So that solves that problem,
Right.
you know?
All right. Um, uh, having made that point about balancing those, supports, flexibility, supports, and making that work, maybe we can jump into one of the questions that was asked, which is, I think, a very interesting question. We won't go into too depth, also due to the timing. Um, but it's a question related to self-limiting and non-self-limiting stress, and I think that's closely related to these discussions. My take on it has always been that uh, if you have, let's say, a failure due to weight, let's say collapse, there's no limit to that. It keeps on moving. While like for thermal expansion, there's a certain limit to that. Like, what is your take on these terms, self-limiting and non-self limiting? Have you ever uh, uh, like, how would you divide them? It's like, what loads would be related to which? What are your
Well,
thoughts?
like you mentioned, and I agree with what you said, that for example, with weight, it's just going to keep going, you know? It's endless. Let's put it like that.
Yeah.
But with the other one, you only are going to move so much depending on the temperature of your piping system. For this
Right.
particular case that we're talking about today, where it's just, let's say, about temperature, that's it. That's what it's going to move.
Yeah.
That's it.
All right. Uh, I think that touches on that topic. Um, having said this, one final question just to wrap things up. Again, feel free to add some new questions to the list in the chat if you have some. Um, just like a summary question, like, do they happen simultaneously? I mean, that was one of the things that confused me in the beginning a little bit as well.
Yeah, they happen at the same time, and that's why it's important to have these separated in three parts, like step one, step two, and step three, like the way that we have it here, because each one, like I said, it's evaluated in a different way. You
Right.
know, for example, uh, weight and pressure, but it's also going to happen with temperature. So you have W plus P plus T. So yeah, it can happen at the same time, and you can also have plus W, which is plus wind. So
Yeah.
the three can happen at the same time. Yes, of course, of
So
course.
even if you would have like a means to measure the actual stress in the system out there, you'd find, let's say, I don't know, let's say a certain amount of stress, then there would be a component of each of these types of stress
Mhm.
in there at that specific moment.
Yes, and that's why with the different piping software in the market, you can, once you have your load cases, you can say, okay, I want to know where this load is coming from, or where this stress is coming from. Then you have the multiple combinations, and then when you do the segregated of in a specific case, then you can see, oh, this issue is just due to temperature.
Yeah.
Then in other cases, you can do the segregated just to see, oh, this one is just coming because of wind.
Yeah.
Because at the end, for loads, if you have W plus P plus T plus, let's say, plus W,
Yeah.
weight, pressure, temperature, and wind, how would you know where this load is coming from?
Yeah.
It would be impossible
Yeah.
because they are all combined. But with the software, you can know, okay, this is because of the weight, this is because of the temperature, this is because of the wind.
Yeah.
You know, so that's why I mean, you have the software. Once you learn to use it, I mean, you can easily identify where does each one of the load is coming from.
Exactly.
Mhm.
All right. Having said that, I would like to wrap up this session. Um, First of all, Juan, I mean, thanks for your time and doing this discussion about primary, secondary stresses. Um, and for all of you out there, I hope you enjoyed it. If this type of content is relevant to you and your team, I invite you to share it with your colleagues and also to connect and follow us on LinkedIn, on YouTube, etc. Subscribe to the newsletter and the contact list of the PSI Association. I know they have like great events, especially in Houston area. And also I invite you to evaluate the Introduction to Pipe Stress course, and then especially the program that is coming up this August. I believe it starts the 2nd of August. It's a 5-week program in which live interactive sessions, virtual sessions with the instructors are mixed with the self-paced modules that are available. So if that is relevant for you, let me just share the link with you in the chat. And I'll also make sure that it is in the show notes of the videos once those are published properly. Um, and for now, have a great day to all of you. And Juan, thanks again for joining. I mean, I had fun.
Thank you very much. It was nice. I think I've never been in a studio like this, so I'm quite happy. I love the microphone. It's so nice. It
Even
looks,
though it didn't
yeah,
work at the
it
start,
didn't
like
work at the beginning, but
we had to switch it.
it's
Yeah.
so nice. I mean, I'm having a good time here. It's so nice to be at Engineering Trainer. We work really close with them. So um, thank you so much for attending this presentation today.
Awesome. All right.
Hope to see you soon.
All right. Have a great day.
Bye bye.